All right. Good afternoon, everybody across the country, and welcome to the first Google Hangout as part of the Habitable Planet online course. This forms first of the series of 3 Google Hangout sessions, and these give you, the students, participants, and basically anyone who would like to take part, the opportunity to interact with and to put questions to the various scientists from the Access program and the Habitable Planet program. Today, we're going to be discussing the physics, and so it's quite a rare opportunity to interact with physicists. As all of us know, most of them never actually leave their office. So today, in honor of the people not leaving their office, I am going to introduce each of the panel with a nugget of what you'd find out about them if you just searched on Google. The first of our panel today, if you search for their name on Google, the first link that comes up is "I'm a scientist, get me out of here." So I'll let them introduce more about themselves.
I'm guessing that's me.
Correct.
Okay, hi everybody. I'm Hayley. If you've been doing the course, you'll know that I gave the lecture on the circulating oceans. My background is oceanography. I'm originally from the UK. That's where I am right now. So I'm signing in from all the way across the world. I did my undergraduate degree in Plymouth, my master's in Southampton, before moving to beautiful Cape Town 4 years ago to do my PhD. And since starting my PhD, I've been involved in the Habitable Planet program in various ways. So.
Okay, thanks, Hayley. Obviously, as you said, you moved from the UK to South Africa, just like me. So I wonder if you maybe tell us why did you choose South Africa, and do you like it, and why?
I absolutely love South Africa. It's been a fantastic 4 years. The reason I moved there was to conduct research into the oceans, because that's what I'm interested in. And as you know, we have we're a very special place in the world with regards to oceans in South Africa, because we have the only place on the planet where a cold and a warm ocean meet. So that's been one of the things I've been studying.
Okay, fantastic. Our next member of the panel, when you look them up on Google, you will discover that their talk for the Habitable Planet online course is by far the most popular and most watched talk. And they might not know this, but this one is Kabir. Hello, Kabir. Don't forget to put your microphone on, Kabir.
Hello.
Hi there. Can you just give us an introduction?
Okay, well, I'm doing my PhD in environmental science at the University of KwaZulu-Natal. Specialize in remote sensing and GIS, with particular focus on vegetation mapping and alien invasives. Also like to include stuff on climate change, and yeah, I'm part of the Access crew. And yeah, we're at the University of KwaZulu-Natal, and we have a nice crowd behind us. And yeah, we look forward to the rest of the talk with you and the rest of the group across South Africa.
Fantastic, thanks, Kabir. And it's really nice to see that you've got a good group there in KZN. I'm impressed. Can you just tell us, and the group there and across the country, give us some reasons why did you think why did you want to go and be a scientist? It's quite an unusual thing to be.
Is that addressed to me or anybody at the venue?
To you, Kabir, you're the scientist.
Well, we have many other scientists here as well, Carl. But yeah, to be a scientist is just something that you know you're passionate about. It grows in you. So I don't really know any explanation or any reason why I want to be a scientist. But it really attracted me. I mean just Earth system science as a whole, and the ability to model the environment and nature, and to explain things in a mathematical way, and just be able to understand the environment is one of the main reasons why I've been interested in Earth system science. I mean, there's so much to learn and so many applications for us to explore. So that's one of the reasons that I can tell you right now.
Thanks, Kabir. It's a really nice introduction to yourself. Really interesting. The next member of the panel I'd like to introduce has, when you search for his name on Google, the first result you get says that he's given hope to thousands of city residents. And that is our Hope. Hope, could you introduce yourself?
Hi everyone, my name is Hope, hailing all the way from Northwest Province. I'm a planeteer and I love science. I aim to be one of the aspiring scientists that South Africa has ever produced. I'm interested in a lot of things, including earth system science, physical science, modeling as a whole, and in general, how can we use science so that we can change the whole world around us? Yeah. Okay.
Nice one. Thanks, Hope. So you're actually the one here who's actually specifically wanted to be a computer scientist. So I wondered, does that mean that you actually prefer working with computers and don't like people?
As it appears so, is that really good with computers. That's what people tend to say. But my main interest in computer science is I believe that computers are the next tool that, the next good technology that we can be able to use so that we can solve so many of problems that are occurring. And so with a computer, we are able to do so many things at once. So my aim and my main interest in computers is so that because they also help us in modeling and because they help us with a lot of things in terms of science. So I aim to take that and use it as a skill set so that we can empower science and we can empower all these models and so forth. So hence my interest sparked in so that to have more interest on computer science. So that's the real reason. And one thing that I found out was that I was quite passionate about computers and all that. So that sort of puts me ahead as an advantage. I mean, you can imagine a physicist who's just a physicist, and then you can imagine a physicist as well who's the one who's very gifted with computers and who really knows what's really, what are the ins and outs of either using computers. Because they say a computer is only as good as the user. So a physicist who has much more knowledge on computer science stands a better chance than a physicist who doesn't have much knowledge on computers. I don't know if you guys get my point, but I realized that since that's my passion, that's why I pursued it as well.
It's a nice story, and I want to tell an anecdote to illustrate that, which was that some years ago, many of you might be aware, that for the first time, a computer managed to beat the world's greatest chess player, and it was hailed as a huge moment in human history that computers had finally beat humans at chess. But actually, the architects of the program, the one that was called Deep Blue, have pointed out. Sorry?
Yeah, Deep Blue. Yeah, I know about the computer.
And they pointed out that it actually wasn't computers that beat a human. It was a human with a tool that beat a human. And the computers really are just tools which extend human ability.
That is true. That is very true.
Okay, everyone, we're still short of a couple of panel members. Professor George Philander from the University of Princeton was due to join us today, but he unfortunately is unable to make it. In his place, we are hoping to, at some point during the discussion, welcome both Hector Shakure, who is a climate scientist at the University of Venda, and Mathieu Rouleau, who is an oceanographer at the University of Cape Town. Both of those we're still waiting for, but I'm going to press ahead nonetheless. What we're going to do from here is I am going to chair a review of what's happened in the course so far. And as we go through each section, I'm going to ask the relevant member of the panel to just give a brief 1-minute summary of what's important from that section to understand in terms of the habitability of the planet. And then I'm going to bring in your questions that are relevant to that. So I want to ask the panel, we've got about 30 questions from you guys to go through. We're keeping an eye on Twitter, right, to see if you guys have more questions that come up. You can just send them to Twitter, or if you're viewing via Google, there's a message window to the right of your screen. So if anything comes up as we go along, you've got Twitter or you've got the Google window. And Dani to my right here is keeping an eye on Twitter to see what's going on. I better press refresh plenty of time. I don't know how often that updates, or maybe go to Twitter itself. So what we'll do is we'll go through in the order of the course. We'll take the questions that we already got from you guys online, and we'll also take any questions from the Google chat on the right, and from the Twitter accounts. To send a question to Twitter, please send it to hashtag HPW16. I believe we have Hector on the line. Hector, are you there? Hector, we can't hear you. Are you there? Hector, hello, hello. He's just getting his headphones out. Okay, hopefully hear from Hector. Can you hear us? Hector.
Hello, Carl.
Hi, Hector. We can hear you. Fantastic.
Great.
Thank you very, very much for joining us at the last minute in lieu of Professor Philander. And could you just please give the viewers a bit of background to yourself?
Interesting. I'm a medical training. That means I'm a weather forecaster. I spent a couple of years on the bench. I was trained in Australia by the Bureau of Meteorology, which is one of the leading bureaus, the training meteorologists in the Southern Hemisphere. And then I went on to practice meteorology as a weather forecaster, and then after that I went on to train weather forecasters in universities. That's after masters, and now I'm just about to complete my PhD. Yeah, so maybe that's a bit of myself for now.
Perfect. Thank you, Hector. That's great. Okay, so we're going to get straight into to answering some of the questions and to giving the review of the course so far. I want to point out that we might not get to everybody's question here today, but all your questions will get answered. If we don't answer your question right now verbally, we will provide you with a written answer. And also, there was a lot of questions that we got that pertain to later stuff in the course. So from Choice, Theon, Tapelo, Daniel, and Prince, I will also provide a written response to you, but we're going to save those questions for when they come up later in the course. Okay, so to get in, if you remember from the very, very start of our week, we had two talks that sort of focused on more astronomy type things. And those were firstly the talk in the beginning that was presented by myself, and then the talk Not Too Hot, presented by Dumasani. And so I'm representing those two, so I'm going to just give you the quick 1 minute summary of both of them. So really, in the beginning, the reason for giving that talk was to firstly show quite how incredibly unlikely it is that you arrived here and are watching this today. And we looked at that problem from the point of view of what are the chances of you having been born, what are the chances of you having survived until this point, and we realized that they're very, very small. But actually to get to be born in the first place requires your parents to have been born. And of course we can follow that all the way back, and through evolutionary history we can come to a realization that every single one of your forefathers and those organisms that preceded humans, right back to the first cells, in every chain, every link of the chain down to becoming you, we discovered that those had to be able to reproduce. So all of your forefathers managed to reproduce at least once, including your parents, which became an uncomfortable concept for many of us. And that takes us back to the start of the life. But we went back even further to ask, why do we have a planet at all? And we came to this idea of the Big Bang, and we looked at the evidence why we think there's a Big Bang in the first place. And that really centers on a thing called the redshift. We had to learn a little bit about radiation, about what radiation is, that it's characterized as a wave, and the idea of the Doppler effect, that the motion of a wave actually distorts the user's perception of it. And so we know that if something's moving away from you, it appears more red, and we saw that everything in the sky is in fact moving away from each other. And that was the first bit of evidence that started scientists onto the track of thinking that at some point, if everything's now expanding out, and at some point at the beginning, everything must have been in one place. That brings me to the first question we have from Keshan Govender, who asks, the Big Bang Theory is based on stars and planets constantly moving away from the center of the universe. As proved by red light diffraction, why can the movement of these planets and stars not be attributed to a theory similar to continental drift, of which one of our continents are constantly moving away from one another? And so I will start on an answer to that. And my answer would simply be that continental drift requires spreading zones as well as subduction zones. And the matter is recycled through the Earth's crust. The universe, on the other hand, doesn't have a crust to recycle the material through. If we had a continental drift style model, material would continually have to be being brought into life at the center of the universe, or being created in order for the universe to expand, and that's not what is observed. But I'd like to throw that open. Does anybody else want to provide an answer? Okay, I'll take that as a no. So, that brings me on to the second talk of our lecture series, which was entitled Not Too Hot, Not Too Cold. In the second talks, we looked at the following observation, that if we now lessen down from the Big Bang and think just about our solar system, we can make the following observation, which is quite interesting. And that's that Mars is furthest from the sun of the three inner planets, but is far too cold. Venus is closest to the sun of the three nearest planets to Earth, but is far too hot. Earth is just right. And so Dumasani posed the question, maybe, it seems from the observational evidence, but maybe, just maybe, Earth is at a habitable temperature because it's a right distance from the sun. And Dumasani did some maths for us. We had to revisit some high school concepts, and one of those is a factor called albedo. The albedo tells you, basically, very simply, that light objects reflect most of the radiation they receive, whereas dark objects absorb it. So dark objects retain more energy if you shine energy on them, and radiation, light, is simply energy. We also had to learn about the conservation of energy, that you only give out as much as you get in. And from those simple laws, and from looking at how much radiation each planet receives from the sun, Venus the most, Earth less, Mars the least because of their distance from the sun, we can then calculate what's called an effective temperature for each planet. And we found out that the effective temperature for Earth should be -18. The average temperature of the planet Earth should be -18 if it was just a ball of rock, the right color, and the right distance from the sun. That's important. Dumasani set up a simple model to test the hypothesis. And we find out that the hypothesis is flawed. Earth should be far too cold. Venus should also be too cold for life. But obviously, Venus is incredibly hot. Mars should be the least, should be the coldest, and is the coldest. But Dumasani's model indicates that there's something missing here. And we start to hint that the thing missing could be the atmosphere. Venus has a very thick atmosphere, Mars has none at all, Earth has just the right one. And so we learned in Light and Air, which I'm skipping ahead a bit, that the atmosphere helps retain radiation on the planet and to keep it warmer. So we have a second question now, which is on that, which is from Mendy via Twitter. And she asks, I'm still a bit confused regarding the size of planets, distance from the sun, and atmospheres. Some clarification. So I'm hoping that what I've just said helps a bit. But principally, if we just take a ball of rock, a given distance from the sun, and we know the color of it, then Venus would be incredibly cold because it's a light color. It reflects away lots of the sun's light. The distance from the sun isn't the most important factor. What turns out to be the most important factor is the atmosphere. And the atmosphere is thickest on Venus. And that's why Venus is by far the hottest. But secondly, you can't have a thick atmosphere if your planet size is too small. And that's where size comes in. Mars is basically too small in order to keep a big atmosphere. So Mars could never get as warm as Venus. Nothing to do with the distance from the sun. Mars could be just as close to the sun. It would never be as hot as Venus. Okay, next we came on to circulating atmosphere and oceans. And so for circulating atmosphere and oceans, I am going to hand over firstly to Kabir to just give us a quick summary of the circulating atmosphere. 1 minute, please, Kabir.
Okay, so circulating atmosphere, one of the main drivers is the unequal heating of the planet of the Earth. As you know, as air rises, it becomes less dense, cannot hold a lot of water, and then precipitation occurs. So as air heats up at the middle of the equator, they circulate towards the poles and become cooler at the polar areas of the Earth, and then circulate back into the center of the equator. So this circulation pattern dictates our rainfall patterns and also dictates where biomes are found. For example, our forest areas and our deserts. And these are as you go into the lectures, you would see that it's highly correlated to our latitude, mid-latitudes, and longitudes. And hopefully you would learn what are the other main drivers of the circulating atmosphere. Just to conclude, the circulating atmosphere is one of the things that keeps our planet cool and habitable for us to live and obviously to survive on planet Earth.
Perfect, thanks, Kabir. Really key point. When we've got planets with an atmosphere like Earth's, the atmosphere, if it was static, would actually make the planet far too hot. Our planet wouldn't be habitable with just a static atmosphere. And so one of the really important things that Kabir's talk actually brings to this is that we need the atmosphere to move and redistribute heat. So without weather, without everything we see around us in the atmosphere, the perturbations, our planet wouldn't be habitable. I'm going to take some questions on firstly the more atmospheric stuff before I come on and ask Haley to deal with some of the more ocean stuff. So I'm going to put to the first question is from Murunwa Makuva, and I'm going to put this to Hector. Murunwa asks, what is the relationship between the Earth's rotation, the Coriolis force, and El Nino? Hector.
Okay, thanks. Now, as Kabir has just introduced, the circulation is a result of differential heating of the Earth's surface due to the intense heating in the tropics and much less heating in the polar regions. You have areas of high pressure created in cooler areas and areas of low pressure created in hotter areas, and therefore air will move from areas of high pressure to low pressure. But once this motion starts taking place, you then have, due to the fact that the Earth is rotating, you then have a force, because the first force that drives motion is the pressure gradient force, and the pressure gradient force drives motion from high pressure to low pressure. But once air is set in motion, it is affected by a secondary force, which is due to the rotation of the Earth. The Earth itself, we know, is rotating. It's rotating at a speed, an angular velocity of 7.292 times 10 to the minus 5 per second, and it completes this rotation in 23 hours and 56 minutes and 4 seconds, make a complete revolution. So because of this rotation, there is an apparent force, and that apparent force which affects moving air is called Coriolis force, and this Coriolis force acts to deflect. It's an apparent force, it's not a real force like gravitational force and the pressure gradient force. So it acts to deflect air to the left in the southern hemisphere and to the right in the northern hemisphere. Along the equator there is no deflection. The Coriolis force is a function of the Coriolis parameter, which is 2 omega sine phi, and the wind speed. And so it is a function. The Coriolis force is affected by two things. It is affected by the angle, the latitude, as well as the wind speed. So farther you are from the equator, the stronger the Coriolis force, as well as the stronger the speed of the wind, and therefore the stronger the Coriolis force. As you move towards the equator, you find that there is no deflection. In the deep tropics, along the equatorial plane, there is no deflection because the equatorial plane itself is parallel to the axis of rotation. So you find that that's how the Earth's rotation is related to the Coriolis force, and with relation to the El Nino, it doesn't quite seem to come here because the El Nino is warming of the ocean in the equatorial Pacific, and this tends to occur along the equatorial plane where the Coriolis force is much weak, and so you find that the Coriolis force is not as strong as you would expect. Would not affect the occurrence of El Nino very much, even though we know that El Nino occurs after a weakening of the trade winds in the equatorial Pacific, which themselves are deflected to the left by the Coriolis force. Carl?
Nice one. I'm here. Thank you, Hector. Oh. Nice one. Does anybody, particularly Kabir or Haley, want to comment? I know would do. Okay. So the next one, and it's also going to be to, I will start with Kabir, is what's the relationship between hurricanes, tornadoes, and El Nino? Kabir?
Yes, I can't answer that right now. Can you take that for me?
Okay, we have a tube coming on at some point. I'm going to save it for him.
Yeah.
Okay.
I can, Carl.
Okay. Yeah.
Carl.
Yes, Hector, go for it.
I can come in there, even though I wasn't prepared for it. But hurricanes, tornadoes. I will talk about hurricanes, which is another name for tropical cyclones as well as typhoons. Hurricanes in the North Atlantic, they are called hurricanes. That's in the area of the United States. And then in the North Pacific, they are called typhoons, and in the Indian Ocean, they are called tropical cyclones. You find that the occurrence of tropical cyclones is also related to the sea surface temperatures. How warm is the ocean, or how cold is the ocean? The minimum threshold is usually around 27 degrees Celsius, 28 degrees Celsius. That's the minimum temperature required for cyclogenesis in several of these basins. But you find that it's not just the sea surface temperature that is important in the formation of tropical cyclones. There is also the circulation. You find that when there's an El Nino, you find that for us, especially in the Southwest Indian Ocean, our cyclones come from the Indian Ocean because that is the warm ocean. The Atlantic is cold, so we can't get cyclones coming from there. But in the Southwest Indian Ocean, we do get cyclones forming, about 9 of them every season. Some do form in the Mozambique Channel. A few cyclones also form in the Mozambique Channel, but they also require the right dynamics. In addition to the thermodynamics, which is the moisture, as well as the temperature, you also need the dynamics, which is the circulation. You need vorticity, cyclonic vorticity, and as well as weak vertical wind shear. And so you find that during El Nino, the circulation is such that you tend to find, do you have subsidence, and you tend to find fewer cyclones forming over the Southwest Indian Ocean. And those few that form, they tend to be driven away from the subcontinent. They tend to be driven towards the poles. So you find that the pattern that we have observed over the years, that during La Nina conditions, for example, we tend to have more cyclones forming, and you also find that these cyclones that form tend to have a westward propagation, which means you are likely to have a landfall or landfalling tropical cyclones during La Nina as opposed to during El Nino. You can go back and look at the history of cyclones that have made landfall. You can go back to 1984. There was Cyclone Domoina, which made landfall in southern Mozambique and affected KwaZulu-Natal. You can go in 1996. You can go to 2000, the most devastating cyclone of them all, Tropical Cyclone Aileen. That was also a protracted El Nino, and there were three cyclones, in fact. Aileen was followed by Gloria and followed by Huda. And then 2001, you also had another cyclone. You had Cyclone Dera making landfall. And so even more recently, 2011, 2012 was another active tropical cyclone season. We had Tropical Cyclone Dando, which flooded Lofeld in Mpumalanga, as well as in Limpopo. And then we had Irina, the famous Irina, which was expected to dump a lot of precipitation in KwaZulu-Natal in March 2012. And so also that was a La Nina. So there seems to be a relationship, just in short, a relationship between the occurrence as well as the tracks of tropical cyclones, depending on whether you are having El Nino or whether you are having La Nina or whether you're having neutral conditions. Carl?
Okay, so I mean, one of the things that I get from that answer is that you guys are in the rest of the country are always complaining that we get bad weather in Cape Town, but we never get any of those here.
You won't get cyclones there. You need to come to Durban if you need cyclones.
Okay, so linking on from that, Henrik Oliver has asked, and it's a question which really I think you can just build on that answer. He asks, with regards to the predicted El Nino event at the end of this year, and by the way, on the ACTIS website, we've made a bit of a note, because at the beginning of this year, in January, climate scientists were predicting that this will definitely be the hottest year on record because of the El Nino event, and we're keen to find out whether that prediction came true. So I'm going to ask that first. Do you think that prediction is going to come true?
I think so. Only we have to wait for the observations to come through. But there are certain things that we expect associated with El Nino, and one of them is warmer than normal air surface and air temperatures, which normally lead to the development of drought conditions. And so there are certain weather conditions which we would expect associated with a weak or strong El Nino, and we do have a developing El Nino, which and it is consistent. El Nino is usually associated with warmer than normal land surface as well as air temperature over southern Africa. And one of the reasons would be the absence of clouds and precipitation.
Okay, thanks, Hector. And then, actually, to Henrik's question itself, it was specifically to South Africa. How is this El Nino going to affect us?
The models, the general circulation models from the global centers, such as the European Center for Medium Range Weather Forecasts, there seems to be agreement with the ensembles of weather forecasts. There seems to be an agreement about the influence or the impact of the El Nino currently obtaining in the equatorial Pacific for the season, but it appears the models are going for a reduced rainfall, especially during the late summer, starting from December, January, February, which is the peak season for the summer rainfall area of South Africa. However, I must hasten to say that the ENSO impact on Southern Africa has been found to be strongest over the eastern sector, and that includes southern Zimbabwe, southern Zambia, Zimbabwe, Botswana, and northern South Africa and central Mozambique. the impact of ENSO events, it tends to be much weaker or to diminish as you move west and further south. And so the impact is expected more over Zimbabwe, the traditional areas, Zimbabwe, southern Zambia, and Botswana. That's where there is the reduced rainfall is expected below normal rainfall. What they normally call below normal, even below normal rainfall, even though the normal is a statistical normal and not necessarily relating to normal weather conditions. I often want to say this to people that normal does not mean normal weather, it means normal in terms of statistics. And so the models in general, the ensembles, the different models that I've looked at seem to suggest that there is likely to be below average rainfall, especially during the late summer, which coincides with the peak of the rainy season. It also coincides with the peak in terms of crop development for the crop growing regions. So that's what the models are suggesting, especially from December through to February, coinciding with the tropical rain belts, the intertropical convergence zone, and also tropical cyclone season.
Okay, Hector, can I very crudely summarize and say that your answer is that ENSO is not so important for South Africa, more for our neighbors?
I think so, yes.
Fantastic. Okay, now probably one of the most controversial questions that will generate some discussion. Both Andrew Hall and Ashley Jalezi both wanted to know, how accurate are climate models? And I'm going to start with Hope, and then I'll throw it open.
Right, thank you, Carl. First off, let me start by saying that climate models are also models, all right? So as you remember on the talk I gave when I said that all models are wrong, but somehow they are useful. And that was actually a quote from GEP Box. So George Box was the one who coined that, was a statistician himself. And statisticians, they work with models all the time. So when it comes to the accuracy of climate models, well, I should say that they are not so accurate. However, like John Tukey said that an approximate answer, to the right problem is worth a good deal than an approximate question to an approximate question to the right, and actually it's an approximate answer to the right question is worth a good deal than an approximate question to the wrong answer. So actually, in essence, they are not so accurate. But however, like for example, we done said that a perfect model is very useless. So they are not so accurate. They are not so accurate to say, okay. But however, they do help us in modeling a whole lot of things. For example, we can be able to model the climate over time and so forth and so forth. So they are not that accurate, but in a sense that makes them useful somehow. For them not to be so accurate or so perfect, that makes them so useful. Yeah. I don't know if there's anyone who has a take on that.
Can I throw that open?
Yeah, I can add a comment, if you like.
Go for it.
Yep. One of the important things I think we can look at to assess whether we would consider climate models accurate, I think it's important to remember that if we're using them as a prediction of the future, we can never test if they're going to be 100% accurate anyway because we don't have access to data from the future. But one thing we can do is apply them to the past and see if they produce the past quite well, which we can do, and we find that they actually don't do too badly. Another thing we can do is take out processes and see what happens then. So one thing they've done, for example, is take out the effect of anthropogenic CO2 emissions and see if the models still produce the same temperature that we see in the observations over the past, and they don't. So using this, you can assume that the effect of anthropogenic, or without the effect of anthropogenic CO2, you can't reproduce the current temperature. So it shows that the models have got the right processes in them, even if they're not producing exactly the right values all the time everywhere. Okay.
Thanks, Haley. Anybody else want to come in? I'll just say from my part, on George's behalf, as he's not here, one of the problems with the models obviously is that they're only as good as the assumptions that go into them, and many of the models tend to assume the same things. And one problem with climate modeling and making predictions for what will happen in 50 years' time is that most of the people who make these models will be dead by the time that their predictions are seen to come true or not come true. So it's more important to them to produce a model that's interesting and a model that agrees with other models in order to get it published rather than one that's correct. Weather forecasting has become exceptionally good in the last few years because weather forecasters get a test every single day. So although it's a complicated modeling process, every day they find out whether they got it wrong or got it right, and they can improve. Climate modelers don't get that. We only have one Earth, and so we can't have a test every day. And as George likes to point out, one of the big tests would be to go back to 6 million years ago. And at 6 million years ago, the world was a lot warmer, had a lot more CO2, and it suddenly cooled down. And the question is, do the models reproduce that if we send them backwards? And the answer at the minute is definitely not. So I would come back to Hope's point that the models, in terms of predictive capacity, have to be taken with a pinch of salt, used as a map, but a map that's not yet very accurate. And therefore, if we have a map that's not very accurate, and we know that there are cliff faces about sensible approaches to walk slowly and carefully. Anybody else want to come in before I move on? Okay, I'm going to head on to the circulating oceans and point out that we built our model now. So we started with a bare rock the right distance from the sun, and we found it wasn't habitable. It was far too cold. Then we added an atmosphere and realized that an atmosphere helps keep it warm, but an atmosphere would make it far too hot if it was just static, and so we brought in weather and climate. And so when we brought in weather and climate, we helped redistribute the heat. But it turns out that the atmosphere isn't enough. We need an ocean to circulate. The ocean, and why we need that, I'm going to give Haley just a minute to talk about.
Okay, cool. Thanks, Carl. So to summarize my lecture, one of the first things we noticed when we looked at a picture of the ocean sea surface temperature was that if you consider the amount of sunlight that comes into the Earth, we know it's most at the equator and less at the poles, you might expect the ocean temperature to match that. And when we look at the sea surface temperature across the Earth, we don't see quite the same pattern as we would expect. We see that there's some areas that are colder than we'd expect and some that are warmer. And we find out through the course of the lecture that this is because the ocean is moving, and that there's a number of different factors that cause the ocean to move. There were 4 of them. I don't know if you can remember. They were the planetary motion, so the way the Earth moves in space, the effects of gravity, which causes things like tides, the wind, which blows across the surface of the water and can move it, and density, which was one very big important one. We saw that there's a giant ocean circulation that helps transport heat and salt around the Earth. And we then use these different methods to explain some interesting things that we see around the coast of South Africa. For example, using our understanding of the wind-driven circulation, we can understand why the west coast of South Africa has a much colder ocean than the east coast. And we saw eventually that this influences things on the land. So we know that the west coast is much more dry, whereas the east coast is much more lush. So we can see that the ocean and the way it moves has a big role in influencing our ecosystems and the habitability of our planet.
Sorry, Haley, I couldn't find my unmute button. I got there. Okay, so I'm going to do some questions on the oceans that we've had. I'm going to quickly start with one from Twitter. Ben Oliver on Twitter asks, and I think Haley, you would appreciate this. Can you tell us about the effect of global warming on sea life?
Yeah, so the effects are quite broad. I mean, you've got, for example, the primary one being warming. So in terms of warming, you have creatures that are used to living in certain water temperatures, and if the ocean water temperature changes, then they may no longer be able to live there. Physically, we expect that the circulation to perhaps change, and that would also then influence the amount of food and nutrients that would be provided for sea life as well. And another often underlooked factor about, well, it's not really related to the warming part of climate change, but more to the CO2 itself, is ocean acidification. Now, you'll probably hear more about this, I think, either this week's lectures or the week after, where the fact that carbon dioxide is absorbed into the ocean changes the pH, which if you're a little creature that's made of something very soft, like chalky material, then you can actually end up dissolving. Things like coral reefs might be really badly affected by ocean acidification. And they'll also be affected in combination by the temperature. So this is going to create a lot of change for animals, and they might not actually be able to adapt quick enough to these changes.
Okay, thanks, Hayley. The next question I want to go on to is from Kathy Drummond, who asks, do the ocean currents play any role in the maintenance of the Hadley and feral cells? If so, how do they influence that circulation? I'm going to go to Kabir first on that, if you want to comment, Kabir, and then maybe Hayley.
Okay, from what I've gathered, I'm not sure, but what I've gathered is that the unequal heating of the Earth is the main distribution or mechanism of the cooling of the planet. Yes, I think to some extent that the oceans do play a part, because that is where the air cools and then comes down and flows over back to the equator, the whole circulating pattern. So yes, the ocean does have a role to play, I would think. However, the unequal heating, especially at the equator and at the poles, are the main drivers of the circulation patterns of the circulating atmosphere.
Okay, thanks, Kabir. Hayley?
Yep. Okay, I would propose that we conduct a bit of a thought experiment here. What do you think would happen if there were no oceans? I imagine that if there were no oceans, it would change the way that the atmosphere would circulate, at least a bit, because the fact that the water is present in the atmosphere as well, which will come from evaporation on the oceans, could change the amount of heating that goes on. So I'm not entirely sure. I would agree with Kabir that predominantly these big-scale circulations will be set up by the unequal heating, but without the oceans, I would imagine you would see a difference.
Okay, anybody else want to comment?
Carl?
Yeah.
Hector? It's Hector here.
Go ahead.
You will find that in the oceans, you find that the western boundary currents are generally warm ocean currents, and the eastern boundary currents are cold ocean currents. And they have a lot to do, like Hayley said, with the distribution of resources. You find that the western sides of continents tend to be drier than the eastern sides, largely as a result of the ocean currents. So to a large extent, the ocean currents determine the distribution, the spatial gradients of rainfall, and also resources and also vegetation from west to east. From our own region, Southern Africa, you find that rainfall is less than 50 millimeters on the west. In fact, it is about 20 millimeters per year in the Namib Desert, which is one of the driest regions on the planet, moving to about 1,000 millimeters over the eastern seaboard, which is considered subhumid. And so you find that the role of the difference in the influence of the Benguela current over the west, as well as the Agalas current over the east. The Mozambique current, which was thought to be a continuous current in not so long ago, is actually now thought of as large anticyclonic gyres rather than a continuous current, which tend to affect also the propagation characteristics of tropical revolving systems, which affect the Mozambique channel. And so if you look at it, I will look at the circulation, because it is not just the the ocean currents influencing the evaporation above the ocean. You also find that the ocean currents act together with the subtropical highs because they are found in the region of the subtropical highs. Most of the ocean currents are found in the area of the subtropical highs, and they are thought to be driven by winds. They are thought to be driven by the subtropical highs. And so over the west, when we look at air which is moving meridionally towards the equator or away from the equator, we consider air to be moving on an isentropic surface which is descending towards the equator and rising towards. It's like an escalator. So air tends to move as if it's on an escalator, descending towards the equator but rising towards the pole. So you find that the subtropical St. Helena anticyclone, which is the South Indian Ocean high, tends to drive air towards the equator, equatorward, and so you find that the air is sinking in the area of the Benguela current, and then air is rising in the area of the Agalas current. So there is some enhanced subsidence in the area of the Benguela current, where you also have the limited evaporation and very limited moisture in the atmosphere. And so there is some kind of relationship between the ocean currents as well as the subtropical highs and how they act together to produce these mean spatial patterns that are observed.
Thanks, Hector. Very nice. Okay, I've got the same question now from two people, and I think it's probably best put to Haley, and that's how big is the role of our oceans when it comes to global warming?
Well, it's quite a funny question, this, because when I was trying to decide what I wanted to do after my undergraduate degree, which was in environmental sciences, I was interested in climate change, and I thought I would study the oceans because of the massive role they play in climate change and in modulating our climate. So, I mean, if you imagine the oceans, they cover 70% of our Earth. They can store a huge amount of heat. They can store a huge amount of carbon dioxide. So the role of them is very, very crucial. The other thing to bear in mind about the oceans, and you'll learn about this in the lecture on the biogeochemical cycling, is that they're quite slow to react. So when the carbon dioxide and stuff gets absorbed into the ocean, it can potentially be locked away for a long, 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 long time. So they act as like a sort of buffer system for mediating like short-term changes. Whilst the atmosphere responds rapidly, and we see that in weather, the ocean responds much more slowly. So I would say a very, very big role to play.
Okay, thanks, Haley. Anybody else want to comment? Anyone there in Durban have any questions?
Peter Maritzburg. No, I think we quite fine. Question.
Sorry, I'm confused too.
Okay.
For some reason, you would believe that UKZN would be in Durban, and I'm aware that science is in Peter Maritzburg, but I always forget.
It's fine. Yeah, I think we're fine. Thanks, Paul.
Okay. All right, one more, and again, the last one for Haley, I think, for a while. In the previous online lecture, I got to find out that there are more nutrients in the oceans with cold water and marine life, because it boosts these in these conditions. This confuses me with the concept of fish production. For example, in Zimbabwe, some of my relatives who do fishing say the winter is when the water is cold, is when fish production is very low. What's the explanation for that? That's from James Nyamhono.
Yeah. Okay, so the general trend of seeing high production in the oceans where you've got cold water typically results because where that cold water has come from is from the depths. And in the depths of the ocean, you've been collecting lots and lots of dead sea life and things. It's like a compost heap. You can imagine it like that. So when that water comes up from the depths, it typically contains lots of nutrients. Now, nutrients aren't the only thing that the phytoplankton, the primary producers in the ocean, need to grow. So in different areas of the ocean, different things can also have an effect. In the Southern Ocean, for example, you have a lot of nutrients and the water's very cold, but you typically don't get as much production as you might expect. And this is because there's another factor there that's limiting. And in this case, it's the micronutrient iron. They don't need very much of it, but there's so little of it in the Southern Ocean because there's nowhere to get it from, no land for dust for it to come from or anything. So the phytoplankton there can't use those nutrients as much as they'd like. In other areas, there's other parts of the ecosystem that eat the phytoplankton, so then they can't grow as much as they can. It's also worth noting that saying somewhere is high nutrient, it might mean that it's high compared to the middle of the ocean, but it might not be as high as, say, the Benguela, where the nutrient load is really, really, really high. So it depends.
Okay, thanks, Hayley. So, I mean, the key, again, to sum up really crudely, is comes down to the difference between water that's cold because it's from upwelled, nutrient-rich water from under the ocean, and water that's just cold because it's winter. That's correct, Hayley?
Yeah, that's true. Although, for example, in Cape Town, you'll actually find that the water is colder in the summer than it is in the winter because of the wind circulation. So depending on the regional dynamics, you might find that the water is not just cold because the air temperature is cold.
Okay, I'm going to move on now to modelling. So when in the course, we went through what we've got so far, and we've actually used models to try and help us explain why Earth's habitable. But we take a bit of a sidestep, and Hope helps us do this, to look at modelling and that as a tool to understanding Earth. And Hope, do you want to just give us a very quick, I know we've already talked quite a lot about models, but just give us a quick rundown. What do models bring to the plate when it comes to understanding Earth's habitability?
Right, thank you, Carl. Models play a big role in us understanding a whole lot of things about the planet. Okay, you remember that models are not limited, and actually they are good tools for us to actually model things, or to actually represent things in another form. So actually, for example, the whole of Earth, if you were to do the experiments on the whole of Earth, I mean, now what you could do as an illustration is you could just draw a circle on a board, and you can start illustrating stuff, say that Africa is over here and all that. So modeling brings it's actually affordable, and then the other thing is model can be wrong, so we keep on improving on all that. And like I gave on my talk that we actually use models to actually so that we can be able to have the final thing. The final thing, for us to have the final thing, we have to play around with models, and models are heavily tested. So there's a lot of testing that goes in through the modeling stage until we get the final thing. So the same thing that goes in with climate models. They're heavily tested before they are being fed to the public, or they're being fed to actually consumers, or to the scientific community in general. So actually, modeling is a very useful tool, and I don't think that science would have progressed so far as it is today if it wasn't for models. So actually, studying of models and knowing more about what are good ways to model and all that also provide good knowledge to the scientific community, and actually helps us to progress and so forth. Thank you.
Thanks, Hope. And so the first question on modelling, and it's quite a nice one, is from Sydney Mutinge. And Sydney asks, what is the science community doing to make sure that model outputs are being communicated to the public in the correct way? I'm not sure how we want to interpret the correct way. I'll let you maybe also define what you think that is. And I'll put that first to Hector.
Hi, Carl. There's been a lot of debate around this issue of communicating the climate community communicating with the user community. There has always been a gap, and you have some really good science coming from the climate scientists, but how is that science communicated, and is it usable science? That's the other question. Is it usable science? Are users, for example, farmers, can they understand when you say that there is a 50% chance of normal rainfall? How can they translate that into action and so on? So there has been a lot of debate. Seasonal forecasting, you may know, in the 1990s, that's when we had the increase in seasonal forecasting the world over, and so it has been improving over the years. But there has been involvement of journalists, for example, involvement of middlemen, because the scientist is not necessarily the person who will go and talk to the farmer. The scientist will do climate modeling and produce results, but it's not necessarily the person who will meet with the user, the end user. And so you find that you have middlemen who are in between, who are also involved, journalists, and also involve, for example, agricultural practitioners who actually work with the farming community, for example, on a day-to-day basis or regularly. And so there has been a lot of involvement, at least here in Southern Africa. A lot of the seasonal climate outlook forums have involved not just the climate science community, but also journalists, for example, as well as agricultural extension officers, in making them understand. Because if you make one journalist understand the meaning or interpret a climate forecast, then they are going to reach out to thousands and millions of people through their publications. And also the agricultural extension officers are going to meet with farmers and explain on and even offer advice about the kind of, for example, crop varieties to grow, whether to grow short season varieties, whether to choose drought resistant varieties, and so on and so forth. And so the advice, which will also come from these extension officers, will need to come from an informed person. And so you find that there has been this realization, and you find that journalists and agricultural extension officers, this is just an example, have been involved and actively involved in climate science, such that they are then able to run the last mile, as we call it. Those people who run the last mile, it's like a relay, it's like a relay. There's someone who will run the last mile, and that person who runs the last mile must run with the correct message. And so you find that we have involved journalists, and a lot of journalists are now able to report with accurate, if it's a probabilistic forecast. If there is a 40% chance of below average rainfall, are you going to go and report in the paper that there is a drought coming, or you are going to find a language that is suitable? So you find that in the past there used to be journalists who were reckless with their reporting, and we used to fight a lot. I was a weather forecaster. I used to fight a lot with journalists who go and write floods forecast, floods expected, when simply I had said there is a chance of heavy rain with a chance of flooding, and this guy will go and put a headline to say that the floods expected. And so we had problems with journalists in the past, but because we have involved them more in understanding the science of weather and climate forecasting, you find that they are doing a much better job today than in the past. And the same with agricultural extension officers, who also play an important role as far as advising for the user community.
Perfect. Thank you very much, Hector. In the interest of time, I'm going to press on. We've only got another 45 minutes. So we're going to we stopped off our little sojourn onto modeling, and we then went on to realize that we'd built up a very good physical picture of the Earth as it is now, but the Earth is constantly dynamic. And in order to understand why the planet's habitable, we need to not only understand how the climate works now, but how it did in the past. And so I'm going to hand over to Haley to give a very quick summary of paleoclimate, and then Hope a very quick one on plate tectonics, please. Haley.
Okay, so hopefully you've all watched Cherie's lecture on this. It's one that I did a while ago, so you'll have to excuse me if my memory isn't quite as good as it should be. So in terms of paleoclimates, one of the things that we learn is that when you build up all the physical parts of the Earth system, they haven't been constant throughout history. So we haven't had the same ocean circulation. The continents haven't been in the same place as they are now. The temperature hasn't been the same. The atmosphere hasn't been the same. Even the amount of sunlight coming in from the sun hasn't been the same. So as much as we're focused on this issue at the moment of climate change, and it's something that is thought of as, something that's very rapidly changing right now, the reality is the climate has always changed in history. And what this means is we can actually use the past as a big thought experiment to figure out what changes the climate and what influences it. So we can account for that in our models now. We can check that it's not some other factor that's causing our current changes instead of anthropogenic CO2. Some of the major things that you learn about in that lecture are the ice ages. which are caused by changes in the orbital rotation of the Earth in relation to its position in the sun, changes the amount of light that comes in, and the heating. You also learn that these ice ages are controlled in other ways. So things like the changes in plate tectonics, which have changed ocean circulation around Antarctica, the Isthmus of Panama, for example, which separated the Atlantic and the Pacific Oceans. These have also changed the way that the temperature is distributed and influenced the ice ages. And one of the main things we learn about this is actually that these long-term climate changes we've seen are very intimately connected with the evolution of life, and in particular humanity. And we learn that our modern civilization has developed in a very, very stable period, really, in comparison to the last 65 million years.
Okay, thanks for that, Hayley. I've got a few questions. Oh, well, firstly, let's just go to Hope. Hope, very quickly, please. Plate tectonics. Actually, Hope, while you give your 1 minute on plate tectonics, I want you to also answer the first question, if that's all right. And it comes from Nkubile Schlotte and Andrew Hall. Both asked basically, does the changing of the grid play any part in the Earth's habitability? So I really think that's what your 1 minute should be about. How does it influence the ice ages, the climate? Why is it important for the Earth's habitability?
All right, thank you, Carl. You remember I gave a talk on continental drift, plate tectonics, and such things as continental drift. And I showed up the graph that represented the change of the climate's temperature over time, as we've seen from 250 million years ago, and how actually the plates appeared as to be they are today. So actually, how did that actually play part in the planet being habitable, or how actually actually our continental drift ocean, the reason for ice age occurrences? It just depends on a whole lot of things, so to say, because besides continental drift and besides circulation of oceans and all that, I mean, the planet as well on its own is a body, and that it's a black body which is receiving radiation from the sun, all right? And you remember that we had to reinvestigate this using plate tectonics to see to it that whether investigating the third part of the energy, which is energy that is trapped beneath the Earth. So actually, like I did show on my talk, that back then we used to have glaciers located within the tropics, but now because the plates have shifted apart, now we find glaciers that they are now only located around the poles. You no longer find them on the tropics and so forth. So actually, plate tectonics as well, because things changed over time, and things, the locations and everything else had to change over time. And then we no longer have continents as just one huge chunk. That played a role in the climate that we see today. So, for example, in the tropics, we know that in the tropics we have hot temperatures mostly. We have climate that is quite full of rain and humid and so forth. In the poles, we have cold climate and all that. So back then, what used to be located in there wasn't the same. So back then, we had there's just one giant continent. So when it comes to the question about, we say that could the Earth's interior composition play any part in making the planet habitable? I would say yes, it does. Somehow it does. It does play a part in the Earth habitable. You can imagine. I mean, some planets like Jupiter. Jupiter's made out of gas. It's totally made out of gas. So hence, planet which is in a gaseous state will not be as much habitable than the one that we have here on Earth. So actually, the interior of the Earth, which allows these continents to drift and so forth, also provide in making the planet more habitable and so forth. Okay. I don't know if there's anyone who wants to add up on that.
Yeah, thanks, Hope. I mean, again, for one of my very crude summaries of what you've said, there's two really important ways in which the plate tectonics actually impacts on the climate. And that's the first is in terms of weathering. Weathering actually controls the amount of CO2 in the atmosphere. So weathering processes take up CO2, and so if there are more mountains, there's less CO2 because there's more weathering going on. But the second and really crucial one from the point of view of the habitable planet story is this changing shapes of the continent. And the changing shapes of the continent changes the way that the oceans are allowed to circulate, and that changes how sensitive the Earth is to things like the Milankovitch cycles, to the amount of radiation that the Earth is receiving. And so, no, the shape of the continent isn't really the primary reason for ice ages. The Milankovitch cycles are the fact that the Earth sometimes gets more or less energy from the sun. But plate tectonics is the reason that the Earth is susceptible to those changes. Is there anybody else wants to add? I'll take that as a no. So the next question on this topic, is another really quite interesting one, is from Mzwendile Sibia, and they ask, do sunspots affect the climate here on Earth? Something we've not talked about at all really in the course, and I'm going to put that to Hector, please.
Thanks, Carl. I'm going to start by defining sunspots. Sunspots are cooler and darker areas on the surface of the sun, what we call the photosphere, and they result in variability of the solar output. The radiation emitted by the sun is affected by sunspots. So sunspots are darker and cooler areas, and they appear once in a while, and they, in fact, there is what is called a sunspot cycle. You tend to have a cycle in sunspot activity, which is around 10-11 years, and the 10-11 year cycle of sunspot activity. And like I said, these areas or darker areas on the photosphere of the sun result in a variability in the output, the solar output, the emission from the sun. And so this, on the other hand, has been found by many researchers to be related to climate variability in many regions of the world. Ourselves in Southern Africa, there is variability at several time scales. We have identified, for example, El Nino Southern Oscillation, which is sometimes a 3 to 4 to 7 year cycle. You also have the quasi-biennial oscillation, which also has about a 2 to 3 year cycle. And then we also have the sunspot cycle. So even our own climate has been found to be related to vary at 10-11 year cycles, which is and has been related to sunspot activity, in addition to an 18-year oscillation which has been found. So for us in Southern Africa, we have called it the quasi-decadal oscillation, the quasi-decadal cycle, which is related to sunspot activity. In fact, some of the variability, some of the worst droughts we have experienced over the subcontinent have occurred at cycles of 10 years. If you go back to 72, 73, go back to 82, 83, go to 91, 92, go to 2002, 2003, go to 2011, 2012, there appears to be a cycle at around 10 to 11 years which is related to sunspot activity. Carl?
Okay, thank you, Hector. That was really nice. So I want to play devil's advocate a bit, Hector. You get these people, climate denialists, or morons for short, who like to say that, you know, this climate change, it's a bunch of nonsense. The climate on Earth here is much better correlated with sunspots. How would you respond to that?
I don't know, because the correlation that we seem to have is droughts. We tend to have droughts with at those cycles related to sunspot activity. So at least for us in Southern Africa, I'm not sure whether I would say sunspots are good for us, considering that.
Anyone else want to comment? Sunspots the reason for climate change? No one?
I guess I would say that if it's, as Hector says, a cycle that goes up and down, then why does the temperature generally seem to be going up and not doing quite the same pattern? So that would just be my kind of throw in there.
I had something to add. It is a funny one. Well, they claim that it's much better correlated. I mean, the temperatures on Earth do go up and down, and at the minute they're on and up, but apparently so are sunspots. But then I guess an important lesson is that obviously correlation doesn't imply causality. Just because two things are correlated doesn't necessarily mean that one causes the other.
This.
Okay, I've got the same question twice on Twitter. Once from Roland Mushi and once from Rehanzu Marivet. And that's, are the continents still drifting? What's the evidence? How do we know? And I'll start with Hope on that.
What's the question, Carl?
Are the continents still drifting? And what's the evidence? How do we know if they are?
That's quite a good question. You'd remember that I'd said on the talk that this is a process that takes a whole lot of years. You can imagine the continent, like for example Africa, the second largest continent on the globe. It's a very huge continent, and so in order for us to monitor if it's moving, it's actually a process that takes a whole lot of time. For example, if you look at that graph that shows that 250 million years ago, that's how we had them chunked up like that, and 250 million years ago, that's actually a substantial amount of time, and over time, they moved apart from each other. So actually, they are moving. However, they are moving at a rate that is very, very slow, that we could detect with the naked eye and so forth. We'd have to have we'd have to project a few million years and so forth. A couple of million years forward, we have to predict them. But however, because of the way they are right now, is that how do we predict which way will which way will Africa drift to? Which way will it be? Will it be askew, or will it drift right, or so forth and all that? So actually, they are moving, because this process still continues. Okay, the process of sea flow spreading and convection currents and so forth, it's still continuing over time and all that. So they are moving, but they are moving at a a very slow rate. So forth.
Yeah, I'd add to that. We were very lucky as Habitable Planet to take a trip to Kenya in 2013, and Kabir was one of the Planeteers who joined us in Kenya, and there we saw that the African continent is actually splitting in two by continental drift. We saw the African Rift Valley, and they use very, very precise measurement techniques to measure the distance between the two sides of the Rift Valley, and they can actually measure, and I think it's, Kabir, I don't know if you can remember, I think it's on the scale of millimeters a year that Africa is tearing apart. Can you remember, Kabir?
Yeah, I can't remember exactly, but I remember the part where I think they use GPS trackers for that. Am I correct?
Yes, I think so.
Yeah, and they place GPS trackers, and as the Earth moves apart, they measure them every tens of years or every year, and they get the difference in. They measure the distance it moves apart.
Okay. And then the other one, and I'll put this to Haley, is I think they also do similar measurements on the seabed. Is that right, Haley?
Sorry, Carl, can you repeat the question that you said?
I think they do similar measurements on the seabed, sea floor spreading.
On the seabed, yes. One of the things they actually do is they use magnetic lines. So at the center there's magma upwelling, and that magma, the iron in it, takes on the polarity of the Earth's magnetic field. And then that, as the ocean spreads, that line of magma moves away from the central rift. And so you can look at those magnetic lines, which they change periodically, the direction of the magnetic field, and you can figure out how long those lines have been moving apart for.
Okay, nice one. Thank you, Haley. I just need to bear with me 1 second. Just bear with me. Okay. So that's the questions on. I'm just checking on Twitter. Sorry. That's the questions on paleoscience. Lastly, I had a miscellaneous section of questions. Some of them are a little bit more light-hearted. So I'd like to throw open the first one. Henrik Oliver again says, I was watching a show on National Geographic about UFO and aliens and people, and the people believed that they helped us build the pyramids. My question is, why would aliens help us build anything in the first place, and what could they possibly gain? Would anybody like to comment on Henrik's question?
Okay, I'd like to have a go first.
Go for it.
Okay. When it comes to the concept of aliens, whether they do exist, there's been a whole lot of drama involved in that, and it came to a point where I was quite convinced that actually aliens were actually created so that the media can have coverage, because that after they were proposed back then, there has been so much of scientific fantasy movies and all that related to aliens and so forth. So with why they helped us build the pyramids, I think came to a point whereby most of the scientists actually couldn't decode much of the pyramids and how they were built. So they had to come to a conclusion that the pyramids were actually built by aliens in terms of how approximate they were built and all that. So that actually we don't have that much of technology to approximate them to approximate the pyramid as much as they are quite approximate. So actually it came to suggesting that actually aliens came here on Earth and they helped us build the pyramids and then they disappeared. But then the pyramids have been in existence for a long period of time, and so far they've been used as a tourist destination and so forth. And they do have a big impact on the history of human beings and how human beings involved and all that. But actually, my take on this is that I don't think aliens helped us build the pyramids, or whether they came here and then they built pyramids and then they discovered that the Earth is no longer habitable for us, it's no longer a good place for us to live in, and they left and so forth. I believe that it's mankind who made the pyramids, and they were made in such a long time ago. The technology that was used for them to be built and all that, we may never have it right now, but we will discover how they were built. Actually, that's my view. That's my take. That's my take on that. So, okay. I don't know if anybody else has another take.
Anyone else? I'd like to propose that the technology they used was called incredibly big whips and lots of slaves. It would seem highly unlikely that aliens would come down, as the question asker says, and just build pyramids. Anyway, I'd like to wrap it up there. As I said, there's a whole bunch more questions that we received, but the rest of them are all pertaining to later things in the course, looking at sustainability, water, biochemistry, astrobiology. It's all stuff that we're really going to discuss in the next Hangout. So I'd like to just go around and see if there are any closing comments from everywhere. I'd like to start first in KZN, and can we just introduce ourselves, those who haven't?
Okay, hi everyone. This is Mobile Shofia. Yeah, I'm here at KZN.
And what are you studying?
I'm doing biological sciences.
So you'll be bored by all the physics then?
Hey?
So you'll be a bit bored by all the physics then?
No, not really. Not really.
Next time it's biology.
Good afternoon, my name is Mohan Lotching. I'm currently doing my PhD at the University of Minnesota, focused on remote sensing of fish infestation.
Thank you. Kabir, any final comments?
No, not that I've nothing major, but yeah, no, I'm good, thanks.
Okay, Haley.
Sorry, I got dropped out there. What were you asking?
Any final comments?
Just that there's lots of people interacting on Twitter, so everybody should definitely check that out. There's a lot of questions that have been asked on there that might be more suitable for some of the later Hangouts, but if they're not, if they're more physics ones, I'll try and answer them over the next couple of days. So.
Okay, thank you. Oh,
Yes, sir. I have a bunch of guys here who were joining me. Actually, there was a pack of them, and then some left. I think but I do have.
Hi guys, my name is. I study here in University of Northwest. I enjoyed the conversation and the topics. It was really fun, and I learned a lot. Thank you.
Nice one, thanks, guys. Hope, any final comments?
Hi guys, my name is Mojale Falfat Pantini. I study here in Northwest University African campus. I really enjoyed the presentation.
All right. I'd like to thank everybody else for tuning in, and the questions are quite really interesting. It really shows that we have a lot of people who are keen and interested in science and so forth. And actually, science is about exploration. We have to keep on exploring, keep on questioning things. Like I say, commandment number 9: always question everything. That's what makes a better scientist at the end of the day. And don't forget that it's not that I'm always right that makes me confident. It's that I'm not afraid of being wrong that makes me confident. So keep on following science, guys. And actually, Earth system science is really fun. So hope to get you guys on the next Hangout. Thank you, Carl.
Thanks, Hope. Fantastic. Hector?
Thanks, Carl. I would like to appreciate the invitation to participate in this hangout, although I was dropped in last minute, and I would like to apologize for having been late as well as not having been prepared for the questions, but I was very happy. I managed to learn quite a lot from this hangout, and I would want to continue to participate in future hangouts. Please don't leave me out in the next hangout. And otherwise, thanks to all of you and to Access for organizing this. I think it is one way in which we can reach a lot of our students. I'm here at the University of Venda, and I think I'm going to encourage a lot of my students to join also, because there is a lot of informative and educational material coming out of this from a whole range of disciplines, and so I appreciate that, and I hope to have more of my students participate in this exciting hangout.
Guys, thank you, Hector. It's been an absolute pleasure to have you, and I'd like to thank all of our panelists today. And everybody who watched, we've had some fantastic engagement on Twitter, and it's been really great to have this group together and meeting, as it were, even though virtually. I just wanted to say that it's been a huge experiment. We have never actually done anything like this before. We didn't know how it was going to go, and I think as Hector and the students there echo, we've had some interesting discussions, and I'm really looking forward to the next one, which will be on biology. So we'll hopefully see you all again there. Thanks very much, guys.